Today, we are opening up the Engineer's Cookbook. We're going to see how treating metal is a lot like following a precise recipe, one that can turn a basic ingredient into something absolutely extraordinary.
So let's kick things off with a little puzzle. Think about a high-performance engine part, like a piston in a race car. How can it possibly be strong enough to handle constant explosions, but not so brittle that it just shatters under all that pressure? Well, the answer to that is all in the art and science of heat treatment. So here's what's on the menu today. We'll start with why we cook metal in the first place. Then we'll get into some recipes for toughness, look at an advanced three-step process, and then cover techniques for softening and stress relief. And finally, we'll see how engineers decide which recipe to use. Let's get right into it.
First up, why we cook metal. I mean, why do we even need to do this? Well, just like a chef wouldn't just serve you a pile of raw flour, an engineer almost never uses a metal in its raw, natural state. It has to be transformed.
And here's the big idea. Heat treatment is all about changing a metal's internal microscopic structure. By very precisely controlling the heating and cooling, engineers can literally dial in the exact properties they want, like making it harder, stronger, or even making it much easier to shape and work with.
All right, let's dive into our first set of recipes. These are all about making materials tougher and way more durable, especially for really demanding jobs.
Okay, so this is probably the most fundamental recipe for toughness out there. I want you to think of it like searing a steak. You apply really intense heat, and then you cool it down super fast. That quick change actually locks the metal's internal structure into a much harder, much stronger state. The result? Something that's incredibly durable.
Now for something a bit more specialized, case hardening. You can think of this as the creme brulee of metalworking. Seriously, the surface gets infused with carbon, which creates this super hard, wear-resistant shell. But the inside, the core, stays softer, which makes it way better at absorbing impacts and shocks.
So why would you do this? Well, it's the perfect solution for parts that just take a constant beating, like gears in a transmission or ball bearings. They get that tough surface to handle all the pressure, but that softer core keeps them from just cracking in half. It's really a brilliant example of that balance engineers are always looking for.
Okay, we've covered some basic recipes. Now let's move on to something a little more gourmet. This is a multi-step process for creating some of the highest performance materials on the entire planet. We're talking aerospace, cutting-edge stuff.
This technique is called precipitation hardening, and you might think it involves even more extreme heat, but it's actually a pretty low-temperature process. It's used on advanced alloys like aluminum and titanium, and the goal is to just dramatically boost their strength and, as a nice little bonus, make them much more resistant to corrosion.
Now, this isn't just a single step. It's more like a carefully choreographed three-act play. You have solution annealing, then quenching, and finally, aging. Each stage builds on the one before it to create a truly elite high-performance material. Let's break down how they work.
The first step, solution annealing, is all about prep work. You heat the metal up to dissolve all the different alloying elements evenly throughout the material. So what does that quote mean? Well, think of it like this. You're turning a lumpy, inconsistent mixture into a perfectly smooth and uniform one.
Next up is the quench, and this step is all about speed. It's a critical, high-speed move. By cooling the metal down incredibly fast, you're basically freezing that uniform structure you just created. You're trapping all those dissolved elements right where they are, creating this super concentrated mix that's all primed and ready for the final step.
And that final stage is called aging. And what's wild is that it happens at a surprisingly low temperature. We're talking about 150 to 190 degrees Celsius. This gentle but sustained heat is what allows these microscopic, strength-giving particles to form inside the metal, finishing the transformation and creating just incredible strength.
So we've spent all this time talking about making metals harder and stronger. But what if an engineer needs the exact opposite? Now we're going to look at the recipes for making materials softer and a whole lot easier to work with.
Remember that steak we seared earlier? You wouldn't just cut into it right away, would you? No, you let it rest, and it gets more tender. Tempering is basically the same idea for metal. After a part is hardened, it can be way too brittle. So this gentle reheating process relieves all that internal stress, creating that perfect balance between hardness and toughness.
Annealing, on the other hand, is what we might call our slow cooking recipe. Its main job is to make a metal as soft and as workable as possible. And this is absolutely essential during manufacturing, when you need to bend, stamp, or machine a part without it cracking. And the benefits here are just huge. I mean, a softer metal means way less wear and tear on expensive manufacturing tools. It's also crucial for removing stresses left over from things like welding, which prevents failures down the road. And hey, as a neat little bonus, it can even improve electrical conductivity.
So this chart really sums up the two different philosophies perfectly. It all comes down to the speed of the cooling. A super fast cool gives you strength, a slow, controlled cool gives you softness and workability. It just goes to show how engineers can achieve totally opposite goals, all by mastering temperature and time.
Okay, and this brings us to the final and maybe the most crucial step. How does an engineer, just like a chef, choose the perfect recipe for what they're trying to make? Well, the choice always comes down to the purpose. It's all about what that part needs to do. For something like a sharp cutting tool, you need maximum hardness. But to easily stamp a car door out of a sheet of steel, you need workability, so you anneal it. For a part that needs to be both strong and tough, like a crankshaft, you harden it and then you temper it.
And this table just ties it all together beautifully. You've got searing the steak for toughness, slow cooking to make it workable, letting it rest to reduce brittleness, and that complex gourmet recipe for elite performance. Each technique is a totally distinct tool in the engineer's kitchen.
So the key takeaway is this: these hidden processes are absolutely everywhere. The strength of the car you drive, the sharpness of a kitchen knife, the reliability of a jet engine, it all depends on an engineer choosing the absolute perfect recipe.
And that leaves us with one last thought. As you go about your day, just look at the metal objects all around you. Your keys, a bridge, a simple paperclip. What kind of invisible properties do they have? And what recipe do you think an engineer used to create them?